Now it's time to show you how to set up your geometry data. Basically what we're going to be trying to show you is how to create indexed geometry. And what this basically means is that we're going to have a set of points or a set of vertices, and then we're going to have to render them in a certain order. So in order to do this, what we're going to need is we're going to need 3 individual variables, which is going to be made inside our app.h. And we're just going to write these right after our DirectX 9 variables. What we're going to need is we're going to need the iDirect3D Vertex buffer 9. And of course, it's going to be a pointer. And we're just going to call this the m_p vertex buffer. And what this basically is amongst many things, it's going to contain the data necessary for each vertex that is going to be a part of our object. So let's say we were just trying to render our simple triangle. It's going to have 3 individual vertices, and this is going to set up the data for those vertices. It's going to contain, everything that our vertice needs to know, essentially, which we'll be able to see better inside our shader. You'll be able to have a better understanding. Next, we're going to create the iDirect3D Vertex declaration buffer, our declaration 9 pointer. And this is going to be our m_p vertex declaration. And what this is going to do is it's going to basically tell our shader that we're going to be using what is our vertex made out of, or not even our shader, moreover just whenever we go to render our data, this is going to say, hey, what is our vertex made out of? What does each vertex have? So for this tutorial, what we're going to have is we're going to be having, naturally where the vertex is in our world, as well as a color that that vertex is going to have. And lastly, what we're going to need is the iDirect3D index buffer, which is going to be the order in which we're going to be rendering these vertices. So we're going to call this m_p index buffer. So with that being said, I've compiled my stuff, and there should be still no breaks or anything like that. What we're going to do is we're going to quickly go over to this image that I had made. So we're going to be rendering a triangle to the screen. And like I said, this is indexed. So what we're going to need is indices for these vertices. So each of these colors is going to be a piece of our triangle. And the numbers are indices. So let's say that we're currently rendering a triangle, and we're going to want it to have actually we want it to be in our world. So we're going to need a position, an X, Y, and Z for each of these little vertices. And then after that, we're going to have to wind them in a clockwise order. What this is going to do is it's going to allow us to see the outside of that triangle, assuming that it was naturally a triangle. But if you were to do it right or counterclockwise, what that'll basically mean is that we'll see it's basically you're rendering it inside out, and that's more OpenGL than DirectX. So going back over into our application, what we're going to do is we're going to go to app.cpp again, and next what we're going to be doing is we're going to be creating our data. So what we're going to need to first do is we're going to start off by filling out the data for our vertex buffer. So we're going to be creating our vertex buffer. And what we're going to do here is we're going to need something to store our vertex data in. Naturally, that's going to be storing it in the buffer, but to have a better understanding of what we're actually throwing in our vertex buffer, we're actually going to go back to app.h, and we're going to create a structure up here. And we're just going to call it vertex structure, whatever. We're going to call it vertex data. And like I said before, our vertices are going to be made up of both a position and a color. So what this is going to be is inside that D3DX that we had included in the last video, there are the vectors. So we're going to want to create a D3DX vector 3. And we're just going to call this position. And then after that, we're going to want to create a D3D color. And we're just going to call it color. Basically what a D3D color is it's the size of a vector 4. So, which would be ARGB, alpha, red, green, and blue. So now that we have our structure, let's go back over to app.cpp. All right, so now that we're in app.cpp, what we're going to do is we're going to create an array. Like I said, we're just going to be creating a triangle. So how many points do we have in a triangle? Well, let's count. 1, 2, 3. So we're going to need 3 vertices. But, however, I just want to point out that if you only have the 3 vertices and you only have 3 indices, you will only be able to see one side of that triangle. Let's say that the triangle was rotating, or we saw the back of that triangle, it would actually be see-through and we wouldn't see it because we haven't actually set it up backwards, which would need to be set up clockwise. We'll explain that more later on. So we're going to create a vertex data array. So vertex data, we're just going to call it vertex data with an underscore v, and do the array brackets and equals, and then we're going to put some curly braces. And now we need stuff to actually put in here. So to set up each one, naturally we know what our structure is going to be. So it's going to be a d through dx vector 3. And now we need to fill in where our vertices are going to be in as far as in our world goes. So what we're going to do is we're just going to set up these vertices negative 0.5f for float, negative 0.5f, and 0.0f. And that's going to be our first vertices position. Next, what we're going to do is we're going to do d through d color underscore. We could do ARGB if we wanted to set up the A value. However, in this tutorial, I am not setting it up to work with alpha values. So we're just going to do XRGB, which based by default, it'll set the A to 255. So the first part is going to be 255 color, because what it does is it ranges between 0 and 255 naturally for your color. So, those are going to be 0 for the color of red, because R is red. Yep. So after that, we're going to close that. And we're going to do end curly brace, end curly brace. There we go. And we're going to put a comma. Let's just go to the next line. And then we're going to actually copy this line. That way we don't have to retype all this stuff out. Makes it a lot easier on ourselves. And what we're going to do is we're going to actually switch this over to 0.0f. This is going to be positive. And 0.0. And then this one's going to be 0. The next one's going to be G255. And basically what we're doing is we're mapping out the triangle. Now these could be in any order that you want. Like I said, I know that I had said that these need to be in They need to be in clockwise order. So like you can still put them in the order of like 0, 2, 1. However, the indices will basically tell it, okay, well this one's first and then this one and then this one. And also this one, the top one doesn't always have to be 0. Like this could be 0, 1, 2, 0, 1, 2, well, however it is that you want to make it. So we have to fill out the last line. So let's just copy and paste that line. Make sure you take out this comma. If you're doing all this by hand, kudos to you. I don't have the patience for that. Got to do this as fast as possible. So we change this over to blue. And now what we're going to need to do is we're going to need to change this vertice to, once again, another point. That way we have our triangle. So essentially what this is doing is this one right here, this middle one, is going to be the top vertice. All right, so imagine, because this is the x, y, and z. So it'd be 0.5 in the x, but 0 in the x, but 0.5 in the y. Then we have negative 0.5 for both the y's of the other one, so they're going to be down here. So this one's going to be here, and this one's going to be here. The third one is going to be over there. And that basically fills out our vertex data. So now for what we're going to need is we're going to need the size of our structure. So make an unsigned integer. We're just going to call this a vertex data size. And we're going to set this equal to how many vertices we have, in this case, 3. So remember, if you add more vertices to this number will change. That number is not going to be 3 if there is not 3 in the array. And so anyway, you're going to want to multiply that by the size of our vertex data. And this is going to give us the size in bytes, basically of this entire structure, because we're going to be actually using this for a little bit longer. So next what we're going to want to do is we're going to want to create our vertex buffer. Well, this was creating vertex buffer. This is the section. This is what we're actually going to physically do. So this is going to create our vertex data, vertex buffer. So once again, what we're going to do is we're going to do m_p device, because this is giving us access to our graphics card. And we're going to do create vertex buffer. And it's once again asking for a lot of stuff. As always, it wants the length. Basically, what you're going to want to send in is the vertex data size, because it wants the vertex data size. Because basically what it wants is it wants how big is this in bytes. So once again, it was 3 times the size of. After that, it wants the usage. And what we're going to want to send in is 0. And then after that, what we're going to want to do is send in D3D FMT underscore index 32. Once again, like I said, MSDN, you can easily search for create vertex buffer, the function, and it'll tell you what all of these do. But this is like the general stuff that you can throw in here. And then after that, you want to send in D3D pool underscore default. And then after that, wants a pointer to a pointer for our vertex buffer, so that way it could fill out our vertex buffer data. So send in the address of m_p vertex buffer, and then after that shared handle, just send in 0, or pointer to shared our handle, send in 0. You don't need to worry about it. And, sorry. All right. And also, if you check what this returns, it returns an H result. So what are we going to do with H results? If check. If it is not equal to s_OK, we're going to copy this assert line, because we are lazy, and it's failed to create vertex buffer. All right, so now if we just fail in creating our vertex buffer, there you go, it'll tell us. So now what we need to do is, assuming that we pass this, we get to the next step, what we're going to want to do now is we want to actually pass this data into our vertex buffer. So how do we do that, you say? Well, this is how. So what the vertex buffer is it, like I said, it is that chunk of data that our shader is going to be using to render out our geometry. So with our vertex buffer, what we're going to need to first do, with any buffer actually, if we're going to be transferring data into our vertex buffer, we're going to need to do we're going to need to follow a certain amount of steps. So with our vertex buffer, I'm just going to copy and paste it. Or actually, no, I'm not. m_p vertex buffer. And we're going to want to lock the buffer. And what this does is it basically locks it from ever being used, that vertex buffer, as far as the GPU goes. That way, we can actually fill in the data. And then after that, we're going to want to, of course, unlock it. So that way the GPU can have it back. So offset to unlock. Basically what this is going to be is you can store different triangles into the buffer. And they can possibly maybe be like different objects. Let's say maybe you had a triangle and its cube stored inside inside one vertex buffer. You can actually offset it X number of bytes, so that way you can actually just get that one little chunk, and that way you're also saving data as well. So that way you don't have like 20 vertex buffers for 20 different objects. You can only use one. But we're going to just send in 0 because we're just storing our triangle and we want to start at the beginning. Size to offset. How big is the vertex buffer from where we're at? Well, it's going to be the vertex data size. And then it wants a void pointer to ppb data. What that basically means is this is going to be a pointer to the beginning, or wherever our offset is, of this buffer. So whatever it gives us in that pointer, that's how much we have access to. So what we're going to want to create is a void pointer. And we're just going to call it temp vertex buffer. Temp is a bad word. In programming, at least. Don't use it. But I want to use it. So what a void pointer is hopefully you know what it is, but a void pointer can be 4 bytes of anything. That's it. 4 bytes of anything. So send in the address of the temp vertex buffer. And then for flags, guess what we're going to be sending in? Like almost everything else, 0. And so like I said, we're going to lock it, and then this is going to return an address basically to our vertex buffer. That way we can fill in the data. So I like to put curly braces around my locks. That way, because it's kind of like a reminder. Because at the end of this, like I said, what we're going to want to do is, I'm going to copy that, and we're going to want to unlock it. Give it back to the GPU. All right, so from there, we now have a pointer to our vertex buffer. So we're going to want to copy the memory. So memcopy, well, that's something, once again, that I hope you're familiar with. All right, so where's our destination? It's going to be that vertex buffer that we're going to be writing to. And our source is our vertex data, which is this up here, because we want to transfer this data into our vertex buffer. How big is it? Vertex data size. And there we go. Now what this should be doing is it should be creating this data, getting the size, create the vertex buffer, and then throw our data into the vertex buffer and hand it back over to the GPU. So from there, we now have our vertex data. It's now over in GPU side and it's good to go. However, we still don't have our triangle. Like I said, we have now just floating vertices, but what is that going to do for us if we don't know what order to actually render them in? So what we're going to need to do next is we're going to need to create the index buffer. And what this is, like I said, it's the indices. So if we have 0, 1, 2, we're going to render it in 0, 1, 2. Like I said, we want to make sure that it is clockwise in relation to where we're looking. All right, so like I said, if we pretend that this was actually turned, like let's say we flipped this triangle, and this 1 was over here, that 2 was over here, and this 0 was, well, still be there. But let's say it was flipped. All right, it would still be clockwise in relation to where you're looking. So it would still be this, that. Just make sure that it's going clockwise. So basically, essentially what this is going to be is the same thing as what we did with our vertex buffer. We're going to need to create data, we're going to need to get the size, we're going to need to call a create function, and we're going to need to lock and unlock sending in the data. However, an index buffer is just unsigned integers. Well, between 0 and however many vertices we have, that's what it's going to be. So we're going to create an index array, or an unsigned int array, equal to some brackets. And now we're going to want to send in, so what are our vertices? So let's go back over to this real quick. So if we look in the order that this is on here, all right, so, whoa, I deleted stuff. Okay, so basically this second one is this one, this first one is this one, and this third one is that one. So what we're going to want to do is this one would actually be 1, that one would be 2, and that one would be 0. So just think of it in that aspect. So what we're going to want to do is we're going to want to go 0, 1, 2, 0, 1, 2, and that would essentially work. You can do 0, 1, 2 because it's clockwise. So 0, 1, and 2. And then after that, what we actually want to do is, like I said, if this is rotating and we end up going to the other side, it's going to be invisible, see-through. We don't want that. So we're going to make this double-sided. We're just going to recycle the vertices. So what we're going to do is we're going to do 0, 2, 1. And like I said, that's in relation to if we were actually behind it looking at it. So it would be 0, 2, 1. It would be kind of backwards. It would basically be the counterclockwise way. So it's pretty weird, but it's pretty cool once you actually understand how it works. So next what we're going to want to do is we're going to want to create another unsigned int for the index data size. Oh, sorry, I'm not actually create index data. All right, and how many indices do we have? We have 6. Woo! So size of unsigned int. Okay, so that's going to give us the number of bytes that this data is taking up. After that, we're going to want to have another if check. We're going to create the index buffer. And we're going to do if m_p the device. And it's going to be create index buffer. I mean, these are pretty straightforward. You know, they tell you the length, once again. Oh wait, sorry. Length is, yeah. Oh boy, index data size. Usage is going to be 0. Next we're going to do d3d fmt underscore index 32. And then after that, d3d pool underscore default. And then it wants the address to our index buffer, so m underscore p index buffer. And after that, 0. So, once again, I mean, it's basically the same thing as we did up here, only it's with the index buffer now. And let's just copy and paste this assert. And failed to create the index buffer. After that, we're going to essentially just copy and paste this. Sorry, but we're actually running short on time for this creation of the data. So quickly, we're going to call this the temporary index buffer. We're going to copy it in these 3 locations. Whoa. Oh wait, sorry, I'm not going to do that. We're going to m underscore p index buffer for the lock, for the unlock, and that's that. I want to do temp index buffer in that address. I want to do it in there. Okay. And also make sure that you get your index data size and replace it out for the vertex data sizes. All right. Oh, and also index data, vertex data. Basically change all the vertex to index. And from there, you now have your index data transferred over into your index buffer. Now lastly, we have one more lone variable, and it is the vertex declaration. Now what the vertex declaration is it's basically going to tell our shader, okay, well, what is each vertex made out of? So we have a vertex that's made up of a position in the world as well as a color. So we have the R, G, and B. So what we now need to do is we're going to need to create our vertex declaration. Well, vertex decal data first off. And what this is going to be is we're going to make a d3d vertex. I'm sorry, d3. Why did I put x? d3d vertex element. Sorry, 9. And we're going to call it declaration. And we're going to do bracket operators equal. Put some curly braces. Now, excuse me, this is a little bit different. What it's going to be is you're going to want to put in essentially which stream is it working on. I think that's what it is. The first one is the stream. Just throw in 0 unless you're doing multi-instancing, which you shouldn't be at this right now at this point. And then the next one is the offset in bytes. So just send in 0 because it's the first part. And then the next part that you're going to be sending in is basically what kind of type is it. So for the first part, well, let's go back and look at our structure. This is essentially what our declaration is going to want to be making. So we're going to be making a vector 3 and a color, which, like I said, a color is essentially a vector 4, but there's also something for colors. So we're going to want to send in d3d decal type underscore, and there's a slew of stuff. But like I said, it's a vector 3. So that's the same thing as a float 3. So d3d decal type underscore float 3. Next, I've never actually put anything else in here, but I would put d3d decal method underscore default. And then after that, what is it used for? You're going to want to send in d3d decal usage underscore position, because it is our position of our vertex, and then send in 0. And then comma. Close that off, comma, and let's just copy this line real quick. So now we need to change a couple of things. So we know that a float 3 is 4 times 3, so it's 12 bytes of data. So in the offset, we're going to need to send in 12 because it's 12 bytes, starts at 12 bytes after the beginning of our declaration. And it's not a float 3 anymore. It is actually a decal type underscore D3D color. Perfect. It's right there for you. And then the usage, you're going to want to change it from position over to color. And there you go. Your declaration data is now set up. Actually, let's get rid of that last comma. Actually, no, just kidding. Keep that there. Don't get rid of it. It'll be bad if you get rid of it. And then there's one more thing you need to call, actually. You need to call D3D decal underscore end. And then you need to call, or you need to put the braces or brackets or whatever. And then that's that. That is the end. You need to do that or else that could cause problems. So basically, you're all set. Now, just a little side note, if you wanted to send in any extra data, usually stuff is thrown in with text chords. But that'll be explained in a later video. It's not going to be explained with the intro to DirectX. So next, we just need to quickly create our declaration. So if m underscore p device, and then we're going to call create vertex. Can we guess what comes next? Declaration. So just send in a pointer to our data. So declaration, that stuff that we just filled out up here. And then it wants a pointer to our declaration. So m underscore p vertex declaration. And is not equal to s underscore OK. And copy over that and failed to create the vertex decal if it failed, if it's not equal to s underscore OK. And from there, you should be able to run it, and guess what? Nothing happens still because we're not done. However, all of our data for our geometry is now filled out. Well, now we have to, create a shader. So here comes the shader portion.